Hello friends, I am Sudipta Haldar and I'm thrilled to have you at AI Tidbits, where we explore AI concepts and techniques using live projects and concrete examples. Today, I'm going to walk you through NCERT Tutor, an EdTech solution I created with a specific problem area in mind. Before jumping into the technology components, I would like to give you some context. There is a significant education gap between rural and urban India, and this gap is not arising out of lack of motivation or talent. It can mostly be attributed to structural and infrastructural issues. We're trying to bridge this gap by providing free online resources that is tailored to run in low bandwidth areas. The curriculum that this solution covers is the most prevalent one in India. It's called the NCERT curriculum. This is followed by all of the central board schools and many state boards. The number of schools following this curriculum are over 31,000, and the number of students covered under this curriculum runs in tens of millions. The essential components that we need to comprise an EdTech solution are two, in my view. The first component, I'm calling it AI Tutor. It does not replace, but augments human teachers. Students can ask questions and get answers from this component. The second component is the quiz component, where the students go to check their exam readiness. They can track their progress by tracking grades over time. They can check the answers, explanations, and get study recommendations. We would see these components in action before jumping into the technology stuff. The component that you are looking at here is the AI tutor. And the students would be asking questions from the curriculum, and the final answer comes from a small language model that's running locally. To provide the final answer, the SLM refers to the sections in the curriculum that covers the same concept that the question is asking about. As you see, there are 5 different sections or chunks that this particular model has referred to. And the student can actually check these sections to see which part of the curriculum covers this particular concept. Now, what do we require to provide a solution like this? We need to create something called a RAG pipeline. RAG stands for Retrieval Augmented Generation. When you ask a question to a language model, it generates a response based on what it knows and based on information it can get from the internet. It leaves room for wrong answers, or what we refer to as hallucinations. When you create the RAG pipeline and restrict the language model to refer to the knowledge base to provide the answers, you can reduce or even eliminate hallucinations. That's what we are trying to do here. Let's go through the steps of creating the RAG pipeline. The very first step is converting the text material, which may be coming in a PDF format, to text format using OCR. I've used a solution called Docling for that. It's a free software. It has been open sourced by IBM in 2024 July. The next step is breaking up this large text into manageable chunks. Those are the chunks you have seen in the previous screen, the AI tutor referring to create the final answer. The language models understand concepts not by these text chunks directly, but by a numerical representation of that. These numerical representations are called vectors. The vector embedding that I have used is provided by OpenAI. It's a model called Text Embedding Free Small. It has 1,536 dimensions. Human mind cannot think in dimensions more than, say, 5 or 6, but our AI counterparts don't have any limitations. If you think 1,536 is a high number of dimensions, let me tell you, OpenAI provides a large model which uses double the number of dimensions. Now, there is a cost differential between these two. The small model costs you 2 cents for every million tokens that you vectorize, while the large model costs you 13 cents. So there is a 6.5 times cost differential between these two models. And you would not be surprised to know that the large model is slightly more accurate. Now, where do we store these vector embeddings? A conventional database or RDBMS is not a good choice. In RDBMS, we do equality searches or range searches. With vectors, we do similarity searches or cosine searches. So we use something called a vector database. I've used pgvector, which comes as an extension to PostgreSQL. I was already using Postgres for something else that I'm going to cover later on, so it was an easy choice. Once these 4 steps are performed, the preparatory work is done. The vector database is ready to be searched. When is the search performed? When the students ask questions. The question that's coming from the users or the students would need to be vectorized in order to find answers or matches. Why that is so? Think of a physics tutor who is monolingual. He understands only English. If you ask him a question in Italian, Deutsche, or Swahili, he would not be able to answer the question. Most likely because he would not be understanding your question in the first place. That's the reason it's essential that the query is vectorized using the same embedding that has been used to vectorize the knowledge base. Once that is done and the searches are performed in the vector database, we would be getting a number of chunks those match the vector closely. I've also used a threshold of 40% to weed out any matches those are weak and not relevant to answer the question. The small language model that I referred to earlier is Ollama. I'm using Ollama 3.1 with 8 billion parameters. These parameters are numerical values or weights that the model uses to understand and express language. And this model is taking in the chunks, those have matched most closely and above the threshold level, and providing the final answer. I told you that this AI tutor would be referring only to the curriculum and would not be answering questions by looking at what is available in the internet. So let's ask it a question, which is the answer to which is easily available on the internet. And let's see whether the tutor is able to answer that. It does not answer the question, which tells us that it's referring only to our course curriculum to provide its answers. This is expected behavior. With that, let's move to the next component, which is the quiz. The best way to see that component in action is to take a quiz. And we're going to take a short quiz of 10 questions. And I'm going to answer the questions and submit my answers. I'm going to submit the answers. It gives a warning that all the questions have not been answered, which is fine. So while we are reviewing the quiz performance, you would notice that every question has been tagged with a chapter and section number and the topic that it covers. For every question, the correct answer would be highlighted in green, and there would be an explanation for the answer. A check mark within a green square tells us that this question has been answered correctly. A red X tells us this question has been answered incorrectly, and the incorrect answer is highlighted in red. A red question mark tells us that this question has been skipped. Now the students can get this study recommendation based on the quiz performance. So these are the chapters from which they have either missed questions or have answered questions wrongly. They can drill down to see which chapters have come up in the recommendation, and also they can look at why. This keeps the record of all past quizzes, so students can easily check their progress and look at the past questions and answers and their explanations and the study recommendations. Now let's look at the technology components, those created this particular solution. The students using NCERT Tutor are interacting with a framework called SANIC. SANIC provides the backend API endpoints and the front end that we just saw. The reason I chose SANIC is because it's very lightweight, requires very little bandwidth, and is extremely scalable. While the students are taking a quiz, there is no need for internet access. The question bank from which the questions come for the quiz is residing on the Postgres database. The question bank, however, was created by 8 different LLMs: AI21 Labs, Anthropic, Cohere, DeepSeek, Google Gemini, Groq, Mistral, and OpenAI. I used a feature called structured output to get the questions and answers from these 8 different LLMs. Now, although I'm referring structured output as one feature, the way the feature is implemented in these 8 different LLMs are slightly different. There are many similarities, but there are nuances and important differences between what kind of validation are required, what kind of strategies you need to interact with them. Now, that is the subject of a different video I'm going to do, and I'm going to leave the link down below in the description. Once the question bank has been created, it lives locally, and there's no more requirement of internet connections. I started this application with the goal of requiring very little bandwidth wherever it runs. What if we want to take it one step further? Can it run in an air-gapped environment where no internet connectivity is there? The quiz component can run. The AI tutor component has one bottleneck. The embedding model that I have chosen requires internet connection to OpenAI platform. Now, this can be replaced with an embedding model of Ollama itself, and that is an item on NCERT Tutor's roadmap. Once that is done, we would be able to run this in a school with just a LAN or any internet access centers or any computer centers, those the government can set up in rural areas with spotty internet connections. For now, NCERT Tutor is getting integrated with the offering of a charitable EdTech organization, which is already doing wonders for students in rural India. If you have any questions or would like me to cover any specific topics or technologies, leave me a comment below. That's all I wanted to cover today, my friends. As always, stay sharp, spread positivity, and have fun. Thank you.